In figures 8.16 and 8.17, we're going to be discussing the size of operator. Now, this operator is actually applied at compile time to determine the number of bytes that an object occupies in memory. In this first of the two examples that we're going to look at, we're going to be applying size of to both an array and to a pointer that points to the first element of an array. Now, you can see here that we have a function called getSize that we've defined. It receives as its argument a double star, a pointer to a double. Now, anytime you see this type of declaration, now you have to consider that the function sometimes may be looking for a pointer to an instance of type double in memory, or it could be looking for the pointer to the first element of an array of doubles. And in C programming, most programmers write double star even when they expect to receive an array of doubles. So you have to look at what the function is supposed to do in the documentation and then pass the appropriate argument based on what the function is supposed to do. So this particular function returns a size t value, which is an unsigned integer value that represents sizes in memory. Now in main, we have a double array with 20 doubles in it. We're going to display the size of the array. When you apply size of to the name of an actual array, it tells you the total number of bytes that are used to store that array. We're then going to take that array and pass it to getSize, and getSize is going to receive it as a pointer to a double, which is a pointer really to the first element of the array. And the thing that we're demonstrating here is that when you apply size of to a pointer, it doesn't matter what the pointer points to. What you're actually determining the size of is the pointer variable itself. So let's go ahead and run this program. And when we see the output here, you can see that the array has 160 bytes in it. And that's because we had 20 doubles, and on my particular computer, a double occupies 8 bytes of memory. So 8 times 20 gives me 160 bytes. On the other hand, when I apply size of to the name of the pointer that getSize receives as an argument, we see that the value is just 4, which is the size of a pointer on my system. So again, when you apply size of to an array's name, it tells you the total number of bytes in the array. When you apply size of to any pointer, it's going to give you the size of the pointer itself, not the data that the pointer points to. And that's interesting because it could be an array of employees, an array of doubles, an array of cards, whatever it happens to be. GetSize in this example, no matter what the type of array is that it receives, would always return 4, the size of a pointer on my system. Now, let's take a look at the next example, figure 8.17. And in this example, we're just going to demonstrate the sizes of various data types on our system. So you can see here that I've declared a whole bunch of variables in main: a character, a short, an int, a long, a float, a double, a long double, an array of integers, and a pointer to an integer which is initialized to point to that array. And you can see here that we're also showing you that size of can be used two different ways, with and without parentheses. When you're doing the size of a data type, you must specify the set of parentheses around the data type name. When you're doing the size of an object, like the variable c, then you can specify size of without the parentheses. However, most people always use the parentheses just because it makes it a little bit clearer what size of is being applied to. So what we're going to do is output for you the size of each item and the size of the corresponding data type. So I have the character c and the size of char, the short integer called s and the size of short, the regular integer called I and the size of int, etc. When we get down to the array, we're going to do size of the array name and separately the size of the pointer that points to that array. So if we go ahead and run this program, by the way, just notice that we got a bunch of warnings here indicating that some variables are not actually being used in the program. That's typical of Visual C++. Anytime you have a variable that hasn't been used, it's going to warn you so that you can either get rid of it or make sure you use it properly. In this example, the only thing we're doing is at compile time displaying the sizes of things, or determining, I should say, the sizes of things. So the character has 1 byte in memory. The size of a character is 1. The short integer has 2 bytes in memory. Size of short is 2. The integer has 4 bytes in memory. Size of int is 4. Notice that on my system, the size of a long is also 4 bytes. The size of a float variable, which is a smaller version of double, takes up 4 bytes in memory instead of 8, is 4 bytes. Floating point numbers that are declared to be of type float have approximately half the precision of double variables. We can see that the size of our double variable is 8 bytes. We can see that the size of long double is also 8 bytes. So on my particular system, there's no difference between an int and a long, and there's no difference between a double and a long double. That is not necessarily the case for every system out there. That just happens to be the case for my Visual C++ running on Windows 7 here. The second to last line here, we see the size of our array is 80. We knew that it was an array of integers, and we know that an integer is 4 bytes, so 4 times 20 elements of the array gives us 80 total bytes. And again, notice that the size of the pointer is still 4 bytes. It doesn't matter what it points to. In the last example, it was pointing to an array of doubles. In this example, it's pointing to an array of integers, and in both cases, the size of the pointer is 4, even though the size of an int is 4 bytes and the size of a double is 8 bytes. The size of a pointer is always the same size no matter what it points to.